Unlock the transformative potential of advanced generative AI models in Site Reliability Engineering, SRE. This course caters to SRE professionals, IT architects, and those eager to harness the full scope of generative AI in the context of SRE. I'll cover the concepts of advanced generative AI techniques to bolster system reliability, scalability, and efficiency in SRE. I'll begin with an introduction to advanced generative AI and SRE. I'll show how to deploy advanced models from Azure AI Model Catalog and transition into testing approaches for applications integrating generative AI. Next, I'll deploy a generative AI-based application to Azure Kubernetes Service, explore the suitability of generative AI models for SRE, and explore SRE tools that incorporate generative AI. With that foundation, I'll demonstrate various methods for supporting SRE operations with generative AI, including chatbots, implementing a back-off mechanism, evaluating model performance, and configuring log analytics for generative AI models on Azure. I'll finish with a discussion on generative AI and SRE advancements, and a demonstration on how to fine-tune generative AI models in Azure OpenAI Studio. At the end of this course, you'll be able to improve the reliability and scalability of IT systems incorporating generative AI. This video explores advanced generative AI. Generative models have emerged as impressive AI-based resources, offering remarkable capabilities in creating new content from text to code to images. Among these models, we have generative adversarial networks, or GANs, variational autoencoders, or VAEs, and autoregressive models. These models stand out for their unique approaches and applications. Azure AI and OpenAI services harness these techniques to offer cutting-edge solutions. This video explores the mechanics of these models and their integration into Azure OpenAI services and the broader Azure AI services. Okay, so we'll start with GANs. GANs consist of two neural networks competing against each other. The generator creates data that mimics the training set, while the discriminator evaluates this data against the real data set. The process is akin to a forger, that's the generator, trying to create convincing fake art, and the art expert, the discriminator, trying to detect the forgery. Over time, the generator improves, producing increasingly realistic data. GANs in Azure and OpenAI platforms are pivotal in tasks like image generation, photorealistic rendering, and even creating art. They can also be used for data augmentation, helping in scenarios where data is scarce or privacy may be a concern. Variational autoencoders, or VAEs, are powerful in encoding data into a compressed representation and then reconstructing it. They differ from traditional autoencoders by introducing a probabilistic twist. They generate a distribution for each encoded input from which they sample to decode. This aspect makes VAEs particularly useful in generating new data that is similar but not identical to the training data. In Azure AI and OpenAI services, VAEs can be leveraged for tasks that require a balance between data generalization and reconstruction. They're used in anomaly detection, where they help identify data points that deviate significantly from the norm. VAEs are also employed in generating synthetic datasets that maintain the statistical properties of real datasets. Autoregressive models predict future values based on past values in a sequence. They are crucial in time series predictions and natural language processing. In natural language processing, they predict the probability of a word or a character based on the preceding sequence, which makes the generation of coherent and contextually relevant text possible. Azure AI harnesses autoregressive models in forecasting scenarios like demand prediction and financial modeling. OpenAI, particularly with generative pre-trained or GPT models, utilizes autoregressive techniques to produce human-like text, offering capabilities for content creation, language translation, and more. Azure AI and OpenAI services incorporate advanced generative AI techniques, including the latest advancements found in GPT-4. This model represents a significant leap forward in the field, providing more nuanced and complex text generation capabilities compared to its predecessors like GPT-3. Azure AI, through its collaboration with OpenAI, enables access to these sophisticated models, offering an expanded range of applications. Azure AI can utilize GPT-4 for advanced natural language processing tasks, enhancing capabilities in areas like sentiment analysis, summarization, and language understanding. Azure Cognitive Services, integrated with GPT-4, offer more refined and context-aware solutions in language translation, chatbots, and customer service automation. While generative AI models offer remarkable capabilities, it's also important to be aware of their potential risks and limitations. These models, just like other forms of AI, lack the capability to autonomously validate or audit the accuracy of their results. They may even create false outputs. Therefore, it's crucial to have mechanisms in place to check and validate the outputs generated by these models. Moreover, there are concerns related to accuracy, privacy, and the potential for misuse of these technologies. For instance, generative AI tools can sometimes produce outputs that may be offensive or inappropriate if not properly monitored and controlled. In terms of evaluating the performance of generative AI models, various metrics are commonly employed. These metrics help validate the output generated by these models and assess their effectiveness in producing realistic and useful results, including concepts like perplexity, precision and recall, inception score, as well as others. Implementing generative AI models in Azure AI and OpenAI services involves several steps. First, the data needs to be cleaned. It needs to be preprocessed and formatted according to the requirements of the chosen generative AI model. Then the appropriate model is chosen. Then these models are integrated with other services for various applications. This video explores site reliability engineering principles and practices. Site reliability engineering combines aspects of software engineering and IT operations. It's an approach that aims to create and maintain highly reliable, scalable, and efficient software systems. It focuses on automating infrastructure, implementing continuous delivery, ensuring system stability, and balancing feature releases with system reliability. Site reliability engineering, or SRE, has become pivotal in managing and ensuring the reliability and availability of software systems and is crucial in cloud environments like Microsoft Azure. The integration of Azure AI and Azure OpenAI services into site reliability engineering practices presents an innovative approach to addressing the complexities of modern software systems. In this video, we explore the synergy between SRE principles and Azure's AI capabilities. So SRE's core principles revolve around proactive management, automation, and continuous improvement of software reliability. Azure OpenAI services can augment these principles, offering advanced tools and capabilities that enrich SRE practices. Azure OpenAI services provides a range of AI models and tools, including large language models, generative models, and other AI-driven solutions. These services allow for advanced data analysis, natural language processing, and automated decision-making, all of which align quite nicely with the proactive and data-driven nature of SRE. Azure OpenAI services can automate and enhance incident response and management. By analyzing system logs and metrics, these AI models can predict potential system issues and automate responses, leading to quicker resolution times and reduced downtime. Integrating Azure OpenAI services with SRE tools enables more sophisticated monitoring and analytics capabilities. AI-driven insights can provide deeper understanding of system performance and user behavior, leading to more informed decision-making in maintaining system reliability. Through Azure OpenAI's advanced analytics and machine learning models, SRE teams can set up intelligent alerting systems. These systems are capable of detecting anomalies and predicting potential system failures before they occur, allowing for preemptive maintenance and intervention, which overall has a positive effect on system reliability. Azure OpenAI services facilitate a continuous learning approach in SRE, By continuously analyzing system performance and reliability data, AI models can suggest improvements, optimize resource usage, and help in refining SRE practices over time. Using Azure OpenAI services within SRE practices also means ensuring the reliability of the AI models themselves. It involves applying SRE principles to the deployment and maintenance of these AI services, ensuring their robustness and consistency. To effectively integrate Azure OpenAI services into SRE practices, organizations should consider some key strategies. First, leverage Azure OpenAI for automated problem solving. Use AI models to automate the identification and resolution of common system issues. Integrate AI with monitoring tools. This helps enhance existing monitoring tools with Azure OpenAI's capabilities for advanced analytics and predictive insights. Use AI for capacity planning and resource optimization. Organizations can implement AI-driven algorithms for efficient resource utilization and proactive capacity planning. They should also ensure AI model reliability. This involves applying SRE principles to the AI models themselves, maintaining their performance and accuracy, and focus on continuous learning and adaptation. For this, organizations can utilize the insights provided by AI models to continuously refine and improve SRE practices. Okay, while Azure OpenAI services offer significant advantages, their integration into SRE practices also poses challenges, particularly in areas like complexity management and skill requirements. To address these, organizations should invest in training and skills development. This ensures that SRE teams have the skills to effectively leverage AI technologies. An organization should start with smaller scale projects to understand the implications of integrating AI into SRE practices. Focus on data quality. Maintain high data quality standards to ensure the balance of AI-driven insights. And finally, while leveraging AI for automation, it's important to maintain human oversight to ensure balanced decision-making. In this demo, we'll deploy advanced generative AI models from Azure AI Model Catalog. All right, for this demo, we'll work in Azure AI Studio. So in the search field, begin typing Azure AI Studio, and when it appears in the filtered list, select it. Now on the Azure AI Studio page, select New Azure AI. Okay, and notice under Azure AI, it says Create an Azure AI Hub. The AI Hub is the top-level resource in AI Studio. It provides data upload and artifact storage, hub-scoped connections to Azure services, including Azure OpenAI, Azure AI Services, and Azure AI Search. It also provides base model endpoints for Azure OpenAI, speech and vision, compute resources, and security and governance. Okay, so we'll leave the subscription at pay-as-you-go, and for resource group, I'll expand the list, and I'll select RG-AI Studio-US East 2. And I'm choosing US East 2 because it's one of the regions where we can deploy some of these advanced generative AI models from the model catalog. For name, I'll call this AI-Hub-Deploy. We'll leave the friendly name as it is. The default project resource group will be the same as our resource group that we specified. Now, I won't specify a description at this time. I'll just select Next Resources. The Azure AI service is named for us. It's going to be a new service, along with the storage account, the key vault. We'll leave application insights at none and container registry at none. We won't use those at all for this demo. So I'll select Next Networking. All right, so we'll leave the public option selected and choose Next Encryption. And note that by default, the system uses Microsoft Managed Keys. Now I'll choose Next Identity, and there's nothing to set here. System assigned identity is selected. I'll select Next Tags. I won't specify any tags at this time. I'll just select Next, Review and Create. Azure runs the final validation. It passes, so I'll select Create. So now at this point, Azure goes and provisions and deploys the resources for my Azure AI Hub specification. Okay, now that that's done, I'll select Go to Resource. And that brings me to the Overview blade for the Azure AI resource. Now I'll select Launch Azure AI Studio, and that opens AI Studio in a new tab. Okay, so now the first thing to do here, make sure that you're on the Manage tab, select New Project. In the Create a Project dialog, I'll give my project the name AI-Deploy and select Create a Project. Okay, and now AI Studio creates the project for us. Now when that's complete, we're redirected to the Overview page for the project under the Build tab. Now I'll select the Explore tab, and that brings me to the AI Model Catalog. Here we'll find many cutting-edge models. At the right side of the page, notice Models indicates that there's 1,625 models here. Now in the middle tile, notice where it says Mistral Large is now available. I'll select View Models to filter only the Mistral models, and note Mistral Large. So I'll select Mistral Large, and that brings me to the Mistral Large page. And here I can find the model details, I can find inference samples, along with sample inputs and outputs. Now just a little background regarding the Mistral Large model. It's the most advanced large language model offered by Mistral AI. The release of Mistral Large on Azure AI Studio is part of a partnership between Microsoft and Mistral AI. It's designed for a wide range of language-based applications that require advanced reasoning, understanding, coding, and text generation capabilities. It includes multilingual support, a generous 32,000 token context window, allowing it to recall precise information from large documents, for example. Another aspect of the model is its coding and math proficiency. It's also equipped with built-in safety features and is protected by Azure AI Content Safety. Overall, the model is suitable for a variety of applications, including internal efficiency, medical terminology, and enhancing productivity and collaboration within organizations. Okay, I'll select Deploy Model. In the Pay-as-you-go deployment for Mistral Large dialog that appears, after reading the terms of use, I'll select Subscribe and Deploy. Now a Deploy Mistral Large dialog appears. We can specify a deployment name. I'll just leave the default and I'll select Deploy. Okay, and now Azure AI Studio deploys the model for us. All right, just be aware that this can also take a couple of minutes. Okay, when that's complete, Open in Playground becomes active. I'll select Open in Playground. And now to show that this is an advanced model on the same level as GPT-4, I'll type a query. I'll ask it, why is site reliability engineering so important? And in a short period of time, it comes back with a very sophisticated and complex answer. All right, well, with that, we've deployed an advanced generative AI model from the Azure AI Model Catalog. In this demo, we'll explore a couple of strategies that can be employed in order to ensure that advanced generative AI applications are reliable. Okay, so first, consider this. Since we pay for generative AI by the token, it's a good idea to incorporate testing of token counts into the SRE practice to understand that form of billing. Okay, so on my development machine, I have Visual Studio Code open with a script named get-completion-tokens.py open. Essentially what we're going to do with this script, we're going to get the completion tokens back from the JSON response, and then we're going to compare that by using OpenAI's very own tokenizer. Okay, so let's explore this code. On lines 1 and 2, we're importing the modules we need for this demo. On line 5, we're picking up the OpenAI API key from an environment variable. On line 6, we're getting the base URL, which is the endpoint, from the environment variable. On line 7, we're setting up the headers. So we specify the API key and the content type, which is application/JSON. Then on line 13, we're asking for input. Please enter your question for the AI. On line 15, we construct the body or the payload of the request. We've got the messages list, the system message on line 17, very simple one. You are an AI assistant that helps people find information. And then on line 18, the user content, and that's the user question that was requested from the user on line 13. Then we set max tokens to 800 on line 19, and then on line 20, we just set the temperature to 0.7. Starting on line 24, we set up the deployment name. That's the GPT-4-base deployment. Then the chat API version. Now, this is such an evolving landscape that you may have to revisit this at some point because they do retire these API versions. Okay, so just keep that in mind. You just have to change it in one place, that's here on line 25, and it will propagate down through the code. Then on line 26, we set up the OpenAI endpoint. We include the base URL, the deployment name, and the chat API version. So this whole formatted string will be the OpenAI endpoint. Then on line 29, we defined send request. So it's expecting an endpoint, headers, body, and I've specified retries in case it needs to retry the request. Okay, on line 31 is where we send the request, and this is the form of an HTTP post request. Now, if the response status code is 200, then we're going to get the response data, and we're going to turn that into a JSON object. On line 36, we extract the completion token count, and that's at response data, and in square brackets, usage and completion tokens. Now, starting on line 39, we navigate through the choices array and message object to extract the content, that's the response, from the AI model. Otherwise, on line 47, we raise an HTTP error for bad response. Okay, down further, on line 51, this is the call to the function send request, and it's going to return two values, the response data and the completion tokens. Then starting on line 54, if there was response data, then we're going to print the response from the generative AI, followed by the completion tokens. Otherwise, we failed to get a response. Okay, so let's go down into the terminal. First, I'll maximize terminal, and I'll type Python get-completion-tokens.py and press enter. And now we get the input request. I'll type describe SRE for me in one sentence. Okay, and the response from generative AI is a good, concise response. Now, the completion tokens, it reports as 35. So let's highlight the response entirely, making sure we get the period at the end of the sentence as well. Press Ctrl-C to copy. Now down to the taskbar, I'll select the browser icon to bring up my browser, where I've navigated to platform.openai.com/tokenizer. And this is OpenAI's very own tokenizer. It's set up for GPT 3.5 and GPT-4. So I'll place my cursor in the enter some text field, and I'll press Ctrl-V, scroll down, and it shows that we have 35 tokens. So we've verified the token count that we got in the completions response. Okay, now one other strategy is to use a third-party tool to verify and confirm the response that you get from the AI model you're using in your application. So let's enter another question. So first I'll run the same script by typing Python get-completion-tokens.py. This time I'll ask, can I use Azure Monitor to track how my Azure OpenAI-based application is performing? ? And the response from generative AI seems like a good one. Notice we have 143 completion tokens. We could check that again, but what we're going to do is we're going to check the validity of the response. So let's highlight the completion response, making sure that we get the period in the last sentence. Ctrl-C to copy, and let's go back to the browser. I'll open a new tab, and in the address bar, I'll type perplexity.ai. Okay, and we can use the free part of this service to confirm what the GPT-4 model just gave us in response. So in the Ask Anything field, I'll type, is this accurate? Shift, enter. Now I'll delimit the content with 3 dashes. So 3 dashes, shift, enter, then I'll press Ctrl-V to paste the response that we just got from the AI model. Shift, enter at the end of the paragraph, and 3 more dashes. And then I'll select the submit icon. Okay, and it comes back and says, yes, the summary is accurate. And then it goes on to describe why. And one of the nice things that I like about perplexity.ai is it actually references the web URLs it used. So for example, I'll select reference 1, and that will open a new tab. And that opens the tab to Microsoft's very own documentation for monitoring Azure OpenAI service. So we've confirmed the accuracy of the statement, but at the same time, we've been provided with reference URLs so that we can double check again with a manual investigation. All right, well, with that, we've explored some strategies that we can use when testing advanced generative AI applications for reliability. In this demo, we'll deploy a reliable and scalable app that integrates generative AI on Azure Kubernetes service. Okay, in this demo, we'll deploy an Azure Kubernetes service or AKS cluster. Then we'll deploy the application. Then we'll deploy an OpenAI service. Okay, so I'm signed into portal.azure.com, but on a second tab, I've navigated to github.com/azure-samples/aks-store-demo. This is a multi-container application and consists of a collection of applications written in different languages and frameworks like Gin, the popular HTTP framework written in Go, Rust with Aaccess Web, the high-performance web framework, JavaScript with Vue.js, and Python with Fast API. Together, these technologies provide the front end for users and store administrators and the REST APIs for sending data to RabbitMQ, MessageQ, and MongoDB database. For my demo, I'm going to use Azure Cloud Shell because it conveniently comes configured with the Azure CLI, the Kubernetes command line client kubectl, and other resources we need for the demo. So back to the Azure Portal tab, I'll select the Cloud Shell icon in the toolbar, and that opens a new bash shell. Now I'll maximize the bash shell. And I like to start with a clean terminal, so I'll type clear. And I'll usually clear between commands. Okay, the first thing to do is to create the resource group for this demo. And to do that, I'll use the az group create command. So I'll type az group create --name, and I'll name it rg-aks-demo --location, and we'll specify East US. Now I'll press enter, and we've successfully created the resource group. Now let's create an AKS cluster. We'll name it AKS-demo-cluster, and we'll place it in the rg-aks-demo resource group that we just created. We'll do this using the az-aks create command. So I'll type az-aks create --resource-group rg-aks-demo-name aks-demo-cluster, and we'll specify --generate-ssh-keys. Now I'll press enter. Okay, it comes back and reports that it's running. Now this can take a couple of minutes. Since we're deploying the application using Azure OpenAI deployed on an AKS cluster, what would be the drivers behind doing that? Well, for one, scalability. AKS supports dynamic scaling, which adjusts the number of pods based on usage, ensuring responsiveness without unnecessary costs. There's cost efficiency because Kubernetes optimizes resource usage, reducing operational costs by minimizing waste and utilizing containers that require less overhead than traditional virtual machines. It's simplified management because Kubernetes automates routine operational tasks like deployments and scaling. It's highly available. There's security integrated. AKS enhances security, in fact, by isolating applications within containers and supporting the enforcement of detailed security policies. Kubernetes also supports a rich ecosystem of add-ons and enables seamless integration with tools for logging, monitoring, and security, which enhances the functionality of our applications. And global distribution. So AKS facilitates multi-region deployment, which is crucial for reducing latency and adhering to regional data regulations when serving global customers. Okay, so the cluster was successfully created. Okay, so now with that done, we need to connect to the cluster. We'll use the Kubernetes command line client kubectl to manage the cluster. Like I said earlier, that's already configured in Cloud Shell. So to connect kubectl to our new AKS cluster, we use the az-aks get credentials command. When we issue this command, it downloads the credentials and tells the Kubernetes client that those are the credentials to use. So in terminal, I'll type az-aks get -credentials -resource-group rg-aks-demo -name aks-demo-cluster. Okay, and that's completed. Now we'll verify that we can interact with the cluster by typing kubectl get nodes. And all three nodes are reporting as ready. Okay, we've successfully deployed the cluster. Now let's deploy the application. So this application includes a YAML manifest that includes all the Kubernetes deployments and services. This includes the product service for showing product information, the order service for placing orders, make line service for processing and completing orders from the queue, a storefront, which is a web application for customers to browse products and place orders, a store admin, which is another web application for store employees, allowing them to view orders in the queue and to manage products. There's MongoDB for persisting data, and RabbitMQ, which is the message queue for orders. Okay, to do that, we'll use the kubectl apply command. So I'll type kubectl apply-f, and I'll specify https://ros.github-user-content.com/azure-store-demo/main/aks-store-all-in-1.yaml. All right, and the output displays the successfully created deployments and services. Now we need to deploy a microservice that uses Azure OpenAI to automatically generate descriptions for any new products being added to the store's inventory. For that, we use a different YAML manifest. I've got it on my local machine, but I've already uploaded it to Cloud Shell. If I do an ls, notice that I have a file named ai-service.yaml. Now to upload it, you just select the file management icon in the toolbar, select upload. That spawns an open dialog, and from there you can search for and upload your own ai-search.yaml file. Now let's have a look at the manifest. So I'll type code ai-service.yaml, and that will open a new inline editor in Azure Cloud Shell. And notice that the YAML manifest consists of two parts. It consists of a deployment and a service within a Kubernetes environment aimed to set up and expose an AI service. Now, I won't spend too much time going over this YAML manifest, but I want to direct your attention to lines 23 down through 30. And that's where we set up the environment. So we have use_Azure_OpenAI on line 23, and we set that to the value true. Then on line 25, we have the Azure OpenAI deployment name, and that's GPT-4-base. Then we have the Azure OpenAI endpoint on line 27. And on line 29, the OpenAI API key. Now these are my values. If you're following along, use your own values. Okay, now scrolling down, we also have the service. Now this defines a Kubernetes service, which is a stable endpoint for accessing the containers. What's important here is that the type is cluster IP, and this specifies that the service will be reachable only within the cluster, and that's on line 44. Ports maps port 5001 on the service to port 5001 on the target pods, facilitating access to the deployed AI service container. And the selector ensures that the service routes network traffic to pods labeled app::AI-service. Okay, now to exit the editor, press Ctrl-Q. And now let's deploy the application with the kubectl apply command. So this time I'll type kubectl apply-f ai-service.yaml. Okay, and the output displays the deployments and services that were successfully created. Now we can test the application. So let's get the nodes again. So kubectl get nodes, and all three are reporting ready again. Now let's type kubectl get pods. And all the pods should have a status of running, and they are. If not, you can reissue the command until they come up. Otherwise, it's off to troubleshooting mode. Now, let's get the IP of the front-end web app for admin and for customer. So to do that, I'll type kubectl get service store-front. Okay, and note the value under external IP. So I'll highlight and copy the external IP. Now I'll open a new tab. I'll paste that IP address in the address bar and press enter. And there's the storefront. So if I go to cart, I have nothing in my shopping cart. If I go back to products, the products listing is as it should be. Okay, let's go back to Cloud Shell. Now I'll type kubectl get service store-admin and note the external IP for the store admin. I'll copy that by highlighting it and pressing Ctrl-C. Now I'll open a new tab, paste that IP address in the address bar, and press enter. And that shows that I have no orders to process. Okay, so now if I go up to the menu and select products, that lists the products. Now I'll select add product. Now for the product name, I'll specify leak-proof puppy diapers. They cost $100. The keywords, I'll use diaper, puppy, leak-proof. Now I'll select Ask AI Assistant, and it will provide a description for me, and it provided a nice snazzy description for me. Okay, I don't have an image, so I'll leave the default specification in the image field, and I'll select Save Product. A notification appears indicating that the product was saved successfully. I'll select OK, and that brings me to the product page. Now if I select Products again, I'll notice that the leak-proof puppy diaper product is now in our list of products. Now, if you've been following along, I would like to caution you, when you're done experimenting with the app, you should delete the resource group to avoid incurring unnecessary charges. If you delete the resource group, it will delete all the resources associated with this demo. Okay, well with that, we have successfully deployed a reliable and scalable app that integrates generative AI on an Aaccess cluster. This video explores the suitability of advanced generative AI models for site reliability engineering practices. Site Reliability Engineering, or SRE, embodies a philosophy of continuous improvement and automation to ensure software systems are reliable and scalable. With Azure's diverse array of AI services, SRE teams can leverage state-of-the-art generative AI models to enhance their practices, from incident response to predictive maintenance. Azure's OpenAI service offers access to powerful models like GPT-4 for natural language processing. This can help in tasks like documentation, analysis, and communication. Azure Machine Learning is a robust platform for building, training, and deploying custom machine learning models that can, among other tasks, predict system failures and streamline resource management. And cognitive services. So Azure provides APIs for computer vision, language understanding, speech-to-text, and more, enabling SRE teams to build intelligent applications relatively easily. Okay, so now let's explore some of the enhancements to SRE practices through Azure AI. First, there's automated monitoring and analysis. So Azure AI can automate the monitoring of systems using predictive analytics to anticipate failures and mitigate them proactively, reducing downtime and improving user satisfaction. Then there's incident management and resolution. Generative AI models can help in the automatic generation of incident reports, suggest resolutions based on historical data, and update runbooks dynamically, making incident management faster and more effective. AI-driven analysis of system usage patterns can also lead to more efficient resource allocation, reducing waste and optimizing costs without compromising system performance. And by continuously analyzing system configurations and logs, Azure AI can ensure that systems adhere to compliance standards and security protocols, automating routine checks and flagging anomalies. Now, some practical application scenarios. For predictive maintenance, generative AI models can forecast potential issues by analyzing system logs and performance metrics, scheduling maintenance tasks before problems affect users. Another application is dynamic configuration and tuning. AI can generate optimal configurations for systems and applications, adjusting parameters in real time based on current workloads and performance goals. It can enhance communication. During incidents, Azure OpenAI Service can be employed to communicate complex technical issues in clear language, assisting in stakeholder management and reducing misunderstandings. Another application is development and QA. Generative AI can produce test cases, simulate user behavior, and generate code, enhancing the development process and quality assurance. Now, as far as suitability, with respect to reliability, generative AI models can greatly enhance system reliability through advanced monitoring and predictive capabilities. This ensures that SRE teams can stay ahead of potential issues. They can enhance efficiency. By automating routine tasks and responses, SRE teams can focus on more strategic initiatives, thus improving overall operational efficiency. And then there's scalability. So Azure's AI services are inherently scalable, allowing SRE practices to grow seamlessly with system size and complexity. Okay, so there are challenges and risks. First, integration complexity. This is a challenge because incorporating AI into existing SRE practices can be complex and requires careful planning and potentially restructuring current processes. There are challenges and risks around data privacy and security. Using AI requires access to data, which must be managed securely and in compliance with regulations, a non-trivial task given the sensitivity of SRE-related data. There's a challenge in acquiring relevant skills. Effectively leveraging Azure AI services requires specialized skills that SRE teams may need to develop or acquire. And then there's cost management. While Azure AI services offer a pay-as-you-go model, they can become costly at scale, which necessitates careful cost monitoring and management. Now let's discuss some concrete examples of how AI in SRE can be applied in real-world scenarios. And we'll start with automated anomaly detection. A global e-commerce company uses Azure machine learning to monitor their website's transactional data. By using machine learning algorithms, they can detect unusual patterns that could indicate a problem, like a sudden drop in transaction volume or an unexpected surge in error messages. These anomalies trigger alerts for SRE teams to investigate, allowing for quick resolution. Predictive scaling with Azure machine learning. So in this example, a streaming service utilizes Azure machine learning to analyze viewership patterns and predict demand surges during popular events or new series releases. The SRE team uses these insights to preemptively scale up infrastructure, ensuring smooth streaming even under high load. This enhances the user experience and helps prevent system overload. And one final example, incident management with Azure OpenAI Service. An IT services provider has integrated the Azure OpenAI service to interpret incident reports written in natural language. The AI service helps categorize incidents and suggests initial steps for resolution based on similar historical incidents, which significantly reduces the resolution time. Beyond Azure OpenAI Service, Azure Machine Learning, and Cognitive Services, Microsoft Azure hosts several other AI-based services that can assist site reliability engineering practices. There's the Azure AI Bot service. This service enables the creation of intelligent, enterprise-grade bots that can enhance customer service and automate common tasks. For SRE, bots could be employed for initial triage of incidents, providing immediate responses to common issues, or facilitating user reports of system behavior. Azure Databricks is an analytics platform providing big data analytics and artificial intelligence capabilities. SRE teams can use it to process large volumes of data, gain insights into system performance, and identify patterns that could indicate potential issues. Other services include Azure Logic Apps. These can help SRE teams automate workflows and integrate systems and services. They can be particularly useful in orchestrating complex operations that involve multiple Azure services and external systems, handling tasks from event response to auto-remediation workflows. Azure Kubernetes Service, or AKS, while not exclusively an AI service, it can be used to deploy AI applications at scale. It can host AI-driven applications that enhance SRE practices, like monitoring tools and automation engines, within containerized environments. And Azure Personalizer is an AI service offering a personalized user experience. In SRE, this could be used to tailor dashboards and incident reports to individual preferences, helping improve the efficiency of monitoring and analysis tasks. There's Azure Search with built-in AI capabilities. This enables the creation of cloud search solutions with built-in AI capabilities that understand and extract insights from content. SRE teams can use this to quickly search logs and documentation for troubleshooting and insights. Azure Quantum. Although quantum computing is still an emerging field, Azure Quantum offers future potential for solving complex optimization problems, which could one day be applied to SRE tasks like resource allocation and traffic routing in ways that traditional computing cannot. And Azure Digital Twins. This Internet of Things, or IoT service, helps create comprehensive models of the physical environment. For SRE, This could be used to model infrastructure and application environments to test the impact of changes in a virtual space. In this demo, we'll support SRE Operations with AI web apps. To get started, I've signed into Azure Portal, and on a second tab in my browser, I've navigated to newrelic.com/sites/default/files/2021-08/site-reliability-engineering-handbook.pdf. This is a publicly available PDF, and we'll use this file as the data source to ground our AI model on relevant SRE information. With this as the foundation of the model, we can create chatbots, web apps, and so on that can really help with task completion, decision-making, and comprehension. Okay, so back to the Azure Portal tab. I'll hover over Azure OpenAI under Azure Services, and I'll select View. On the Azure AI Services page, I'll select OpenAI-Demo-CA East, and that opens in the Resources Overview blade. I'll right-click Go to Azure OpenAI Studio, and I'll select Open Link in New tab. Now in the New tab, it opens to Azure OpenAI Studio. Here in Azure OpenAI Studio, we'll select Bring Your Own Data. And on the Add Data dialog that appears, I'll expand the Select Data Source list, and I'll choose Upload Files. Okay, so I'll leave the subscription as it is at Pay As You Go. For the Blob Storage resource, I'll select Create a New Azure Blob Storage Resource, and that opens to the Create a Storage Account page in a new tab. I'll leave the subscription as it is, and for Resource Group, I'll select Create New, and I'll name it RG-BYOD-CA East. Next, I'll select OK. Now for Storage Account name, I'll name mine Blob Store ABC123. And for region, I'll expand the list and I'll select Canada East. Now for performance, I'll leave the standard option selected. And for redundancy, I'll leave the default geo-redundant storage selected, and I'll choose Next. We won't change any of the advanced settings, so I'll just select Next. For networking, we'll leave the Enable Public Access for All Networks option selected, and I'll choose Next. Now we'll leave the defaults for data protection, and select Next again. For encryption, we're going to leave the defaults, and note that by default, the encryption type is Microsoft Managed Keys. I'll select Next. We won't specify any tags, I'll just select Next again. Azure does the final validation. Everything appears to be fine, so I'll select Create. Okay, now Azure goes and provisions and deploys the resources for my storage account. Now let's go back to Azure OpenAI Studio. For the Blob Storage resource, I'll select the refresh icon. Now I'll expand the list, and it picked up the new storage account that we created, so I'll select it, Blob Store ABC123. For Azure OpenAI to access the storage account, we need to turn on cross-origin resource sharing our cores. So I'll select Turn on Cores. I'll select Create a New Azure AI Search Resource. That opens the Create a Search Service page in a new tab. I'll leave the subscription as is. For Resource Group, I'll expand the list, and I'll choose the one that we just created a couple of moments ago, RG-BYOD-CA East. For the service name, I'll name mine Azure Search ABC123. For location, I'll expand the list and select Canada East. And the pricing tier is standard. I'll select Next Scale. Okay, so now this is important. Note that as it is right now, the estimated cost for this resource is going to be around $250 a month. So this is why I'm adding all the resources to the same resource group, because when I'm done, I'm just going to delete the resource group, and it will delete all of the resources within that group, including the search service. Okay, now I'll select Next Networking. By default, public networking is selected. I'll select Next Tags. I won't specify any tags at this time. I'll just select Next, Review, and Create. Now Azure does the final validation. It's successful, so I'll select Create. And now Azure goes and provisions and deploys the resources for my Azure AI Search Service. Okay, now that's done, I'll go back to the Azure OpenAI Studio tab. I'll select the refresh icon beside the Select Azure AI Search Resource field. I'll expand the list, and it picked up the resource that we just created. So I'll select it, Azure Search ABC123. We need to specify an index name. I'll just name mine Index ABC123. Now I can't add vector search to this search resource, so I'll just select Next. Okay, and now we need to upload the file. So I'll select Browse for a file. In the open dialog that appears, I'll select the Site Reliability Engineering Handbook PDF, and I'll select Open. Now I'll select Upload Files. Okay, and the file was uploaded successfully. Now I'll select Next. We'll leave the search type and the chunk size at their default levels and select Next. Now on the Review and Finish page, I'll select Save and Close. Okay, so now the data is being ingested and the index is being created. When this is done, we can start exploring Azure OpenAI capabilities with a no-code approach through the chat playground. Okay, so now that's done, but first, before we do anything further, I'll expand Advanced Settings and note this setting: limit responses to your data content. With this checkbox checked, it means that any queries that we place will be limited to the data content. So our answers will really be grounded in the SRE handbook that we uploaded. All right, so let's submit a prompt to generate a completion. I'll ask, what is an error budget? And the model comes back with a relevant answer. An error budget is a metric that defines how unreliable service is allowed to be within a specific period, and it provides me with a reference from where it obtained that information. Just imagine that we had several files that we uploaded. Well, if it referenced all of those files and various parts of those different files, then they would be listed here as references as well. Okay, so now that we know it's working the way that we want it to work, the AI model is firmly grounded in our data. Let's select Deploy To at the top of the page, and I'll choose to deploy to a new web app. The Deploy to a Web App dialog appears. We'll leave the Create a New Web App option selected, and for the name, I'll name it SRE Coach. For a subscription, I'll expand the list and choose Pay As You Go. For the resource group, I'll select the resource group that we created earlier, RG-BYOD-CA East. For location, I'll put this in Canada East. And for a pricing plan, I'll select Basic B1. I won't enable chat history in the web app. I'll just select Deploy. Okay, and now it's deploying the web app. Just keep in mind that this can take a few minutes to complete. Now, when that's done, a message appears indicating that the web app was deployed, so we can select Launch Web App. So I'll select Launch Web App, and we're redirected to a page that indicates that authentication is not configured yet. Now, this can take a few minutes to apply, so just wait a few minutes and either select the refresh icon at the top of the browser window or press F5 like I've done, and then eventually it'll come up. Okay, so now we can start chatting. I'm going to ask the same question. What is an error budget? And it comes back with the answer: an error budget is a metric that determines how unreliable a service is allowed to be within a specific time frame. So the same as before, and we have the same reference as before. Okay, so the idea here is to support SRE practitioners as they perform their SRE tasks. So now, with this deployed as a web app, we can then deploy it as a bot and to various channels like Teams, Slack, and others. Okay, so with that, we've successfully supported SRE Operations with AI web apps. This video explores SRE tools and platforms with advanced generative AI. Azure DevOps services incorporate advanced generative AI capabilities, particularly under the umbrella of AI Ops, which stands for Artificial Intelligence for IT Operations. Used in this manner, it can enhance incident management and monitoring. This integration of AI into Azure's cloud platform and DevOps processes aims to make the Azure platform more self-adaptive, resilient, and efficient. AI Ops supports engineers in taking effective and timely actions to improve service quality and enhance the customer experience. Now let's consider some key aspects of Azure's AI Ops implementation. First, AI-driven cloud service management. Azure has developed AI solutions in collaboration with Microsoft Research to make cloud service management more efficient and reliable. AI Ops teams work across Azure engineering teams to address the increasing scale and complexity of cloud services and the ever-changing customer needs. This approach helps cloud engineers make data-driven decisions and automate actions as part of the cloud services or DevOps processes. Azure's cloud services incorporate capabilities for self-monitoring, self-adapting, and self-healing with minimal human intervention. This automation, powered by AI and machine learning, not only improves service quality and efficiency, but also enhances customer experience. Furthermore, it boosts DevOps productivity by empowering engineers with insights, thereby reducing the need to manually address repetitive issues. Okay, now the methodology for building AI Ops solutions. Azure's AI Ops solutions start with data collection from systems, customers, and processes. The methodology involves detecting current problems, diagnosing their causes, and predicting future issues, and optimizing or adjusting to mitigate these issues. These actions are driven by business metrics like customer satisfaction, system quality, and DevOps productivity, either fully automated or with human intervention as needed. Azure has introduced AI Ops solutions for system management automation, which includes hardware failure prediction and proactive actions like live migration. Additionally, AI solutions in DevOps include improved incident management with AI-based solutions enabling early detection of issues, engagement of the right teams, and rapid mitigation to reduce customer impact. Azure has developed a system for the safe deployment of infrastructure components to identify and prevent latent issues. There's also a focus on improving the customer experience through AI solutions, like decision support systems guiding customers to appropriate support resources. Azure has built systems like Resource Central, an AI serving platform that collects telemetry, learns from past behaviors, and predicts future behaviors of Azure's compute workloads. This system helps in accurately predicting resource procurement and allocation, thus improving system performance and efficiency. To summarize it all up, Azure DevOps services are leveraging advanced generative AI capabilities through AI Ops to enhance incident management and monitoring. This includes AI-driven cloud service management, improving service quality and efficiency, a robust methodology for building AI Ops solutions, AI for systems and DevOps, safe deployment, AI for customers, and optimizing cloud resource usage. These efforts are geared towards making Azure more adaptive, efficient, and customer-centric. In this demo, we'll improve site reliability by implementing a back-off mechanism. All right, to begin my demo, I've signed into Azure Portal. So I've been working with an Azure OpenAI service resource, and so it appears under my recent list on my Azure Portal homepage. I'll select the Azure OpenAI resource named OpenAI-Demo-CA East, and that brings me to the overview blade for the service. Now I'll right-click, go to Azure OpenAI Studio, and select Open Link in New Tab. Okay, so Azure OpenAI Studio opens in the new tab. Now select Deployments, and with the GPT-4-base deployment selected, I'll choose Edit Deployment. Now in the Edit Deployment dialog that appears, I'll expand Advanced Options. And this shows that my tokens per minute rate limit is set at 10,000, and I've enabled Dynamic Quota. So this should give me lots of capacity to perform most normal types of chat completion interactions with the GPT-4 model. Okay, so I'll select Cancel. I'll go down to the taskbar, and I'll select the Visual Studio Code icon. I have a Python script named SRE-backoff-mechanism.py open. In the script, from lines 1 to 3, we're importing the modules we need for the demo. Then from lines 6 down through 18, we're configuring the API key, the base URL, the headers, and the body of the request. Notably, in the messages list, I have a system message. You are an AI assistant that helps people find information. That's on line 14. And on line 15, the user content. In one sentence, can you describe back-off mechanisms in the context of SRE? Line 21, I set up the deployment name. On line 22, I set up the Chat API version. Line 23, I set up the OpenAI endpoint, and that includes the base URL, the deployment name, and the Chat API version. The whole formatted string on line 23 is what comprises the OpenAI endpoint that we use to send the request. Line 26 is the function definition, send _request _with _backoff. It's expecting an endpoint to be passed, headers, body. I set retries at a default of 5, and the backoff in seconds I set at 10, and I'll explain that shortly. On line 27, we set up a loop for the retries. On line 28, we send an HTTP post request with the endpoint, the headers, and the body. Now on line 30, if the response status code is 200, then all is well, and then we navigate through the choices array and the message object to extract the content of the response. The next part of the if statement, the elif, on line 40, checks whether the response status code is 429. A 429 status code indicates that the rate limit has been exceeded. So on line 41, we display a message to the user that the rate limit has been exceeded and it's going to retry in the number of backoff seconds. Then line 42, we implement the backoff by calling time.sleep with the backoff in seconds. Then on line 43, we're multiplying the backoff in seconds times 2. So the first time through the loop, with the backoff originally at 10, the next time it goes through the loop, it will be 20. Then the next time after that, it will be 40, then 80, and so on. Now, if we don't get any response, then we raise an error on line 45. Okay, on line 50, this is where we call the send _request _with _backoff function, passing the OpenAI endpoint, headers, and the body. Now, if there is response data, then we print it out, and that's on line 53. Otherwise, we print out a message, failed to get a response after several retries. Let's run the program. Down in terminal, I'll maximize the terminal window, and to run the program, I'll type Python sre-backoff-mechanism.py and press enter. Okay, and we get the chat completion response back. Obviously, we haven't hit the rate limit at this point. Let's go back down to the taskbar. I'll select the browser icon to bring up the browser. Now I'll select Edit Deployment again, and I'll expand Advanced Options. I'll disable Dynamic Quota, and I'll move the slider for tokens per minute rate limit to the farthest left-hand side, where it's at 1,000 tokens per minute. I'll select Save and Close to save the changes to the deployment. Now let's go back to Visual Studio Code. I'll run that program again. Okay, so this time it works. Now I'll up arrow to quickly bring that command back. I'll press enter to run it again. And now we see that the rate limit was exceeded. So it retries in 10 seconds. And that won't be enough because it's got to at least wait for 1 minute. So it's retrying and it retries again and comes back with retrying in 20 seconds, then 40 seconds, and it will keep trying until enough time has elapsed so that we don't breach the rate limit or the number of retries has been exceeded. And we set the number of retries at 5. So the next time through will be 40 seconds. And when you add 40 to 20 to 10, that's more than a minute. So that should be more than enough. And it will come back after the third time through the loop and the 40-second wait time. Overall, what we've done here is we've improved site reliability by implementing a backoff mechanism. And this helps to avoid rate limiting errors in generative AI applications. In this demo, we'll evaluate a generative AI model's performance in Azure AI Studio. Okay, to start my demo, I've signed into Azure Portal. Since I've recently worked with Azure AI Studio, it appears in my Azure Services list. If it's not in your list, just search for Azure AI Studio in the search bar and select it from the filtered list. Meanwhile, I'll select Azure AI Studio from my Azure Services list. So I've got an AI hub named AI-hub-eval. So I'll select AI-hub-eval, and that brings up the hub in the overview blade. We're going to set up the evaluation in Azure AI Studio. In AI Studio, we'll be able to log, view, and analyze detailed evaluation metrics for our AI model. Under Govern the environment for your team in AI Studio, I'll select Launch Azure AI Studio. Okay, so this brings you to the Manage tab and the Details page. Now, the first thing we need to do is set up a new connection. So I'll select New Connection. In the Add a Connection to External Assets dialog that appears, I'll choose Azure OpenAI AI Models. Now, a Connect an Azure OpenAI Resource dialog appears. It comes up with the Browse Resources option selected, and underneath it displays one resource. So I have one resource. It's named OpenAI-Demo-CA East. For authentication, I'll leave API key selected, and on the right side of the dialog, I'll select Add Connection. Then I'll select Close. Now on the Overview page, under Connections, it may not appear right away. If that's the case, just select View All. That opens the Connections page where it does appear. So now going back to the Details page, now it appears in the list under Connections. Okay, so now we'll create a new project. So I'll select New Project. In the Create a Project dialog, I'll give the project the name AI-eval, and I'll select Create Project. Now Azure provisions and deploys all the resources that we need for the project. Okay, and now that that's done, over in the left menu, I'll select Evaluation. I'll select New Evaluation, and we'll do a question and answer with context evaluation. On the right side of the page, there's the option to download a data template for the selected scenario if you need it. We can also set the evaluation name. We'll just leave the default. And I'll select Next. Now I'll select Add Your Data Set. I'll select Upload File. And in the Open dialog, I'll navigate to my demo directory, and I'll select the file named QA_with_context.jsonl. This is the testing data set that I've created for this demo. Now I'll select Open. And back on the Create a New Evaluation page, the top 3 rows are available for us to preview. I'll select Next. Now for performance and quality metrics, we'll choose groundedness, relevance, and coherence. In the tile for each of these metrics, there's a brief description indicating what it's used for. Okay, under Connection, I'll expand the list. I'll select the OpenAI Demo-CA East connection that we created earlier. And for deployment name or model, there's only one deployment connected to the Azure OpenAI resource the connection is based on. So I'll leave GPT-4-base selected. There's also risk and safety metrics, but we won't choose any of those metrics for this demo. Below that, there's a section that allows us to map our data set to the evaluation input. Now, the way that I've designed the data set, I've made it a one-to-one mapping. So context in the data set equates to context as expected by the evaluation run. The same with answer and the same with question. Okay, so I'll select Next. Now review and finish. Everything looks good. So I'll select Submit. Okay, that brings us back to the evaluation page. If the evaluation doesn't appear right away, select Refresh, and it should appear in the list. So now it appears. Notice the status says Not Started. We can drill down into the evaluation, so I'll select it. And on the Explorer page, I'll expand Logs, Azure ML, where we'll find 3 files. These 3 files play a unique role in the evaluation process. Executionlogs.txt contains detailed logs related to the execution of the evaluation run. It may include information regarding the start and end times of the evaluation, any errors or warnings encountered during the run, and other diagnostic information that can help us understand how the evaluation proceeded. Then there's promptflow-automatic.log. This log file is associated with the automatic runtime environment used by PromptFlow in Azure AI Studio. The automatic runtime is a feature that provides required computing resources for the evaluation. And promptflow-service.log. This file contains logs generated by the PromptFlow service itself. This log is useful for understanding the behavior of the PromptFlow service during the evaluation run and troubleshooting any issues related to the service. Each of these log files are updated in real time during the evaluation run. Okay, so now let's go back to the evaluation page. Okay, the status is still not started. And then the status transitions to running. And then completed. So now let's drill down into the evaluation again. And on the Output tab, we have the Performance and Quality Metrics dashboard. There are the 3 metrics that we selected: groundedness, relevance, and coherence. and their scores. And scrolling down, we can even see the details with respect to each question within the dataset. Overall, the evaluation provides some pretty comprehensive insights into the AI model's capabilities and limitations. All right then, with that, we've successfully evaluated generative AI model performance in Azure AI Studio. This video considers generative AI and SRE advancements. Okay, we'll start with a brief overview of generative AI. Generative AI refers to a subset of artificial intelligence that is concerned with creating new content, whether it be text, images, or even code. Transformer models are the cornerstone of modern natural language processing and machine learning. These models are trained on large volumes of text to capture semantic relationships between words, which is one reason why they can generate text that closely resembles human responses. Transformer architecture comprises two main blocks, encoder and decoder blocks. The encoder creates semantic representations of the training vocabulary. The decoder generates new language sequences. Common transformer models include OpenAI's generative pre-trained transformer models like GPT-4. Other notable AI models use techniques like generative adversarial networks or GANs, variational autoencoders or VAEs, and autoregressive models. These models essentially learn patterns and features from large data sets and then use this understanding to generate novel outputs. It's worth noting, though, that OpenAI's more publicized and widely used models rely primarily on transformer models. Azure's AI-based services support generative AI applications. Azure Machine Learning, for instance, offers a robust platform for training and deploying AI models, including generative models. The Azure AI platform's scalability, combined with its powerful computational resources, makes it an ideal environment for handling the large data sets and intensive processing requirements of generative AI. All right, now let's turn to generative AI with site reliability engineering. So, site reliability engineering is a discipline that incorporates aspects of software engineering and applies them to infrastructure and operations problems. The main goal is to create scalable and highly reliable software systems. It involves practices like monitoring, automation, and designing for reliability. Azure provides tools and services that align well with SRE principles. Azure Monitor and Azure Automation, for instance, offer capabilities for monitoring cloud resources, automating tasks, and ensuring the reliability and efficiency of services. Azure's infrastructure also supports the quick deployment of robust, fault-tolerant applications that are essential in SRE practice. The integration of generative AI with SRE presents a unique opportunity for Azure-based technologies. This integration can lead to more efficient and reliable systems and provides an innovative approach to problem solving in both fields. Generative AI can predict potential issues in software systems, leading to proactive maintenance. Azure Machine Learning can be used to train models that predict and identify system anomalies. Combined with Azure Automation, these predictions can trigger automated workflows to address issues before they escalate. Generative AI can augment SRE by enhancing monitoring capabilities. AI models can analyze logs and metrics to detect patterns that might indicate system degradation. Azure Monitor can be seamlessly integrated with these AI models, offering a comprehensive monitoring solution that helps in quicker incident response and resolution. Generative AI models can simulate various load scenarios to test the resilience of systems. Azure-based technologies can leverage this to perform sophisticated load testing, ensuring that systems are reliable and performant under different conditions. Generative AI can help innovate problem solving. It can assist in generating novel solutions for complex SRE challenges. Azure Cognitive Services, for instance, can provide AI-powered insights that can be instrumental in devising innovative approaches to reliability engineering. While the integration of generative AI and SRE within Azure cloud-based technologies offers numerous benefits, it also presents challenges. Ensuring data privacy and security, managing the complexity of AI models, and ensuring the ethical use of AI are some of the key concerns. Azure does provide tools and frameworks to ensure the ethical use of AI, however. It's crucial to maintain transparency, fairness, and accountability in AI systems, especially in generative models that have a wide range of applications. As generative AI models become more complex, Azure's cloud infrastructure must continue to evolve to support these advancements efficiently. This includes optimizing computational resources and ensuring the scalability of AI applications. Embracing continuous learning and adaptation. The field of AI is continually evolving. Azure-based technologies must keep pace with these advancements, incorporating the latest research and innovations into their platforms. This requires a commitment to continuous learning and adaptation. In this demo, we'll configure log analytics for generative AI resources. Okay, I've signed into Azure portal. The first thing we need to do in order to set up log analytics is to create a log analytics workspace. And to do that, we navigate to log analytics workspaces. In the Azure portal, I can start searching for log analytics in the search box, but it's already in my Azure services, so I'll select log analytics workspaces. I'll select create. I'll leave the subscription pay-as-you-go. For resource group, I'll expand the list, and I'll choose RG-LA-CA East. This is a resource group that I created earlier just for this purpose, and it's in Canada East. It currently has no other resources in it whatsoever. Okay, now we give the log analytics workspace a name. I'm going to name mine LAWS Demo, and that stands for Log Analytics Workspace Demo. Again, the region, Canada East. Now, there's a reason behind this. According to the documentation, not only is it important to choose a region that supports log analytics, obviously, but it's also advisable to choose a region that's close to the data sources that you plan to collect the data from. And the Azure OpenAI resource that I'm going to collect the data from in this demo is in Canada East. Okay, I'm not going to create any tags, so I'll just select Review and Create to go directly to Review and Create. Final validation passed, I'll select Create. Now Azure provisions and deploys my Log Analytics workspace. Okay, and now that that's done, I'll go back to Portal Home. To analyze logs and metrics data with Azure Monitor Log Analytics queries, we need to configure diagnostic settings for the Azure OpenAI resource. So under my recent resources list, I'll select the OpenAI-Demo-CA East Azure OpenAI resource. Now I'll scroll down, and under Monitoring, I'll select Diagnostic Settings. I'll select Add Diagnostic Setting, and I'll name this Diagnostics 1. Under Logs, for category groups, I'll select All Logs. For Metrics, I'll select All Metrics. For Diagnostic Details, I'll select Send to Log Analytics Workspace. I'll leave the subscription pay-as-you-go. I'll expand the Log Analytics Workspace list, and I'll select the LAWS Demo Log Analytics Workspace that we just created. Now I'll select Save, and we've successfully updated the diagnostic settings for this resource. Now I'll go back to Portal Home. I'll drill down into the Azure OpenAI resource. Scroll down. This time I'll select Logs. In the list of logs, I'll select the LAWS Demo Log Analytic Workspace that we created. Now I'll select Logs in the left menu. When the query window appears, I'll close it. And now we can perform some Kusto queries here. But we need to create something to log, right? So let's go down to the taskbar. I'll select the Visual Studio Code icon to bring Visual Studio Code up. Now in the terminal, I'll run the file named sre-backoff-mechanism.py by typing Python sre-backoff-mechanism.py and pressing enter. Okay, and we get a response from the generative AI. Now, I've set the token rate at its absolutely lowest level in the deployment for this demo. So I'm going to up arrow to bring that command back and run it again, and we should get a 429 error. And we did. The rate limit was exceeded, so it's going to retry in 10 seconds, then 20, then 40, and so on. Meanwhile, we'll let that run. We'll go back to the browser, and here we are in the Log Analytics workspace. And what we'll do is we'll create a Custo query here. What I'll do is I'll start typing Azure Diagnostics, and it appears in the autocomplete list. Now I'll specify take 100, and that will give us 100 lines of information. Now, if I run this at the moment, it probably won't show anything because it takes a couple of minutes for the logs to propagate throughout the system. So I'll select Run, and as expected, no results found from the last 24 hours. So what we need to do is wait 10 to 15 minutes, then we'll see some diagnostics data. Okay, so after waiting approximately 15 minutes, I'll select Run. And now this time, the query returns a couple of results. If I expand them, I can see the tenant ID, the time generated, resource ID, category, resource group, subscription ID, and so on. Then if I expand properties_s, I can see the API name, the model version, the request length, and so on. And something important is the result signature. That's 200. So that means this request returned OK, and obviously did return some results with the response length. Now I'll check the next one. So I'll expand it, and it looks pretty similar, except this time, notice the result signature is 429. So this is the event when we ran the Python script and it exceeded the rate limit. All right then. With that, we've successfully configured Log Analytics for generative AI resources. In this demo, we'll fine-tune a generative AI model. To start my demo, I've signed into Azure Portal, and I'm on my home page. Under my recent resources list, I have an Azure OpenAI resource named OpenAI-FT-SW Central. FT for fine-tune, SW Central for Sweden Central. It's one of the regions where you can train GPT 3.5 models. Okay, so I'll select OpenAI-FT-SW Central, and that opens the resource to the overview blade. Notice the location, Sweden Central. Now I'll right-click on Go to Azure OpenAI Studio, and I'll select Open Link in New Tab. Okay, so now let's go to the new tab where we're in Azure OpenAI Studio. Now I'll select Models. And before we start any fine-tuning, I'm just going to set some column options. So in the toolbar, I'll select Column Options, and in the Edit Columns fly-in, I'll uncheck Status. I'll check Fine-Tune, and I'll check Fine-Tune Retirement Time, and I'll select Save. On the right-hand side, notice the Fine-Tune Retirement Time. So we want to avoid GPT 3.5 Turbo model version 0613 because its retirement time is in June 2024, whereas the other GPT models 0125 and 1106 are both slated for retirement for fine-tuning in December 2024. So we'll go with version 1106. Okay, then let's get started. In the toolbar, I'll select Create a Custom Model. In the Create a Custom Model dialog, for a base model type, I'll expand the list and I'll choose GPT 3.5 Turbo 1106. I won't specify any model suffix. I'll just select Next. Now for training data, I'll select Browse for File, and in my demo directory, I have training and validation data. I'll select the training data and note that this is a JSON-L formatted document. It's UTF-8 with a byte order mark. So I'll select training-data.jsonl and I'll select Open. Now I'll select Upload File, and the file is successfully uploaded. Now it appears under Choose from Existing Files. Now, I'll need to upload the validation data. So I'll select Next. I'll select the Upload Your Local Files tab. I'll select Browse for a file. This time I'll select the validation data.jsonl file and I'll select Open. Now I'll select Upload File. And now the validation data has also been uploaded and both appear under Choose from Existing Files. So I'll select Next. For advanced options, we have number of epochs, which is the number of times through the full training set. We have the batch size, and we have the learning rate multiplier. I won't change any of the default settings. I'll just select Next. Now, there's not much to review. I have uploaded the training data and the validation data. The base model appears. I'll select Start Training Job. Okay, and the training job begins. And notice now under Models, there's a new tab, Custom Models. And notice the status of our training job right now is pending. Now, if that doesn't transition to running within, say, 5 minutes or so, just select the refresh icon on the toolbar. And note now the status does say running. Okay, so the training job is running. Now, I have to warn you, this can take quite some time. This model, in fact, took over 30 minutes to train. Okay, and after a little over 30 minutes, a notification appears indicating that we've created the fine-tuned model. If your models page doesn't show the model that's fully trained under custom models, just refresh the page. So I'll press F5. And now the model appears. Now if I select the model name, the information on the page shows that training succeeded, and the total training time was 36 minutes and 34 seconds actually. And the training hours billed was 0.25 hours. Now scrolling down under training results, I can see the training loss versus validation loss. And scrolling down further, I can see individual training events. All right then, well, with that, we have successfully fine-tuned a generative AI model. So in this course, we've examined techniques to improve the scalability of IT systems incorporating generative AI. We did this by exploring advanced generative AI, site reliability engineering, complex generative AI models, and advanced generative AI reliability. We explored the scalability of applications incorporating generative AI, advanced application of generative AI models for site reliability engineering, site reliability engineering tools and platforms with advanced generative AI. We also configured log analytics and diagnostics for generative AI models. We discussed advancements, and we fine-tuned and optimized a generative AI model. In our next course, we'll move on to discuss the ethical and responsible use of AI in IT.